of mass, then what is the cost incurred by the transportation action? So the cost is defined according to the underlying metric space, so which is the L1 or L2 distance or something else. And that gives us the general cost function between these any 2 points. And the second term is the amount of mass being transported. So that's basically your transport plan. How do you plan to transport the mass from the first set to the second set in such a way that it minimizes the total cost incurred by you? Yes. So in this case, I have drawn a simple diagram which sort of shows how this thing looks for the discrete case and finite support setup. So we have only 3 points in our red set, and you have only 2 points in our blue set. And the blue items have 1/2 mass each, and the red items have 1/3 mass each. So as you can see that the total mass in the two sets balance out. And the distances between the 2 points are given by this x minus y norm distance. And the green lines indicate the amount, the transport plan, or what is the flow, the min cost flow between the points. So we want to optimize this flow, which is also same as finding the minimum distribution in the previous formulation. So of course, this should be the planned flow should be subject to capacity constraints, as in the total flow. Let's say the red points are the destination points. So the total flow going into the red points cannot exceed the capacity of the red point. So 1/6 has to be equal to 1/3 or at least less than that. And similarly, the total flow going out of the blue point cannot be greater than the amount of mass at the blue point. So these are the capacity constraints, which are similar to what we said about the marginals being, the distribution with the marginals being equal to mu1 and mu2. So another way in which I usually view this is to have this cost matrix corresponding to these two sets. So if the cardinalities of the set are, let's say, n, then we have an n square matrix, and we have a transport plan which is also n square. And then if we do a dot product between two matrices, that gives us the cost of the entire transportation plan. So now this cost matrix is usually specified by the application domain. And in the min cost matching setup, in the discrete case, in the uniform mass case with the equal cardinality setup, this ends up as being a permutation matrix, which lines up the elements of the red set with the elements of the blue set. So let's look at some applications in the machine learning domain. So this is a very, I think this paper has 2000 citations by now, and this is a very popular diagram these days. So this was the application called word mover distance, where it was a 2015 paper, and you are given two documents or two sentences, let's say, which have a set of words in them. Now you want to compute the similarity between the two sentences. And the problem is, of course, that it's very rare to have the same word in two sentences, but even different words can have the same implicit meaning. So how do you factor that in? And the way to do that is well known. It's the word embedding technique, where you can see that since it's an earlier paper, Obama is being mapped closer to president. This is no longer true. But the embedding for speaks is closer to greets and so on. And the similarity between those two sentences would be the sum of the minimum mapping between the words in each of the sentence in the embedding space. So you basically are taking away the stop words, and you're representing each sentence as a set of word embedding vectors. And you have a underlying metric where you have a specification of the distances between the embeddings. And now you want to find the distances between the two sets of word embeddings. And the distance gives you basically a notion of similarity between the two documents. So this is I just gave credits to the author here. And so, as I said, this problem was like thought about in the late 90s, early 2000s. And in those days, people started by looking at the image similarity setup, where you are representing the images by a set of points, and the points exist in the red, blue, green space. So it's the three-dimensional space. So you have two images, and corresponding to those two images, you have a set of point clouds in the 3D space. And you want to minimize this distance between those two point clouds. So it's obviously a very low dimensional setup. And the later word mover distance application was a much higher dimensional setup, and that made things more interesting as well as challenging, as we'll see next. Another application was our earlier paper where we did graph matching, where you can represent each graphs as a set of embedding. The embeddings are node embeddings, and then you want to find the distances between the graphs by computing the distances between the two sets of node embeddings. So we'll move on to the later application of search, but if you have any questions till now, please ask. Okay.
Hello.
Yeah. Right.
Indra, in the image similarity example, in addition to conservation constraint, we may also need to enforce some kind of smoothness constraint, right? Like a block of pixels in image 1 should map to block of pixels in image 2. Does OT allow that kind of constraints as well?
Okay, good question. I am not sure, but I think so. SC, last time you were asking something about hierarchical constraints in OT domain. Is there any relation to that?
I don't know. I mean, maybe Lokesh is asking more about if the domain is ordered, then there should be some smoothness along that ordering. In standard earth mover, discrete earth mover, there's no, the order of the words is unimportant, but maybe there are other situations where you don't want too much discontinuity in mass transported as you move along the I and J spaces. I don't know which one he means.
I mean the second one, like as we move along IJ, the transportation plan should be sort of continuous.
So Lokesh, just to this question sort of reveals the connection with some of the findings that we have in our previous graph matching paper. So Indra, honestly, do you remember that we have this case that even if two nodes are matching, two edges are not matching, right? And vice versa. So I think this is the same thing. So one of the way, Lokesh, to incorporate this is but I mean a possible way is that you just translate the embedding of of a pixel or a particular portion of the point, so that the embedding itself kind of reflects the neighborhood. Okay, and then you try to match embeddings try to match the images in the embedding space. Then you can get some benefit. Did you understand what I will say?
Yes, sir. So you mean we need to embed the RGB values of each pixel in the image?
Either RGB values of each pixel may be too much, but some kind of neighborhood embedding should be there, so that at least the neighborhoods are preserved.
Yes, sir. Yeah.
Right. Okay. So now that we have an idea of the basic EMD based application, so it is in our interest to compute the earth mover distance as quickly as possible and as accurately as possible. So in the k nearest neighbor search setup, you have this corpus of items. So let's think about it in terms of documents. So we have this document corpus represented by the blue squares, and each document can be visualized as a distribution, like we have just discussed, a distribution over the words. So let's say you have these n distributions, mu1 to mu_n over some d-dimensional space. That's our corpus dataset. And now you're given the query represented by this red item, and you want to find the closest item in the dataset to this given query, or maybe the k closest items. So now let's say you don't care about scaling, you just want to find the best answer. Then you would use exact computation techniques, and you would linearly scan over the entire data set. You would sort the scores and you would get the most similar key items. But obviously this does not scale to large databases. So people have come up with a host of approximate algorithms which have this sort of time complexity versus accuracy trade-off. Now, here there are a bunch of these algorithms, and I have actually jumped ahead and pasted a table from the results here so that we can have some idea about the numbers. So as you can see at the right hand, towards the right of this, let's say array, we have the order n square algorithms, which are much more accurate than the linear time approximations. But, of course, there's that trade-off. So in the table to the rightmost part, you will find the exact solution time complexity. So this thing is basically what time complexity you would get when using a min cost LP solver. So we are so just to clarify the setup, in this paper they have this set of corpus and query items, and they have computed the time over the same data set with each of the techniques. So the upper bound for exact computation is something like this: 41.5 seconds and 154 seconds in the MNIST data set, and so on. Now we have this in the order n square algorithms. We have this very popular algorithm called Sinkhorn, which does so we are not going to discuss the details in this talk, but sufficient to say it just takes an initial transport plan. It takes an initial matrix, and it does iterative row and column scaling. So first it scales it does a softmax over the rows, and then it does a softmax over the columns, and it keeps doing this iteratively until the marginal constraints are satisfied. It reaches some sort of a steady state. So the Sinkhorn are quite accurate despite being approximations, but they're order n square algorithms because you are operating on a matrix. And you can see that although the time computation is order n square, it still falls to around 10% of the earlier time, exact W1 computations. So let's now look at the other end of the spectrum. So when the word mover distance guys were proposing this application of EMD in the text similarity search domain, they were very aware of the computational costs, and they proposed a couple of heuristics. So the first one was this means technique. So here they simply just decided to collapse each of the distribution into a single point to take the mean, and then they just computed the distance between the two. So it's a very crude approximation, but it's super fast. You can say it takes hardly any time to run. The other approximation proposed by the WMD guys were this relaxed WMD measure, where they simply take the first set and then they map each element to the closest point in the second set. So it's very obvious that it won't satisfy any mass constraints. It just finds the closest projection in the other set. Again, so that's an approximation, but it's still quite fast, as you can see. The ACT1 paper was a follow-up paper in 19, which tries to add some mass constraints to this relaxed WMD work. So it became a bit slower, but then it gave increased accuracy. We will discuss quadtree and flow tree today. These are our major discussions slated for today. So as you can see, they fall somewhere in this range. Flow tree is, so all of these, okay. So all of these till flow tree are linear time algorithm. You can see that there's a significant jump between flow tree and RWMD. So RWMD starts going into the n square computational space. And okay, TF-IDF is something that is well known in the text domain. It's not applicable to the image, so there's no result there. And overlap simply computes the overlap between the set items. So if they have a common item, if the two sets have a common item, it contributes to the overlap similarity score. So it's some sort of a Jaccard metric. And yes, so this is the whole host of approximation algorithms, which is currently, which are popular today. So Yeah. So one thing to so a couple of comments on this. So the first thing is that so let's take the cost matrix. Okay, the cost matrix that we specified here. Now there is no constraint that this cost matrix has to come from an underlying metric. It can be arbitrarily specified, and so so it may be a non-metric which specifies the cost matrix. So in that case, you don't have any other option but to specify the entire thing and go for an n-square algorithm. But if we have the prior knowledge that the cost matrix is derived from this underlying metric, which has some properties, distance properties, then the idea or the goal is to avoid specifying the cost matrix completely. Because as soon as you specify that n-square matrix, you have lost the battle with respect to scalability. So you want to avoid specifying the cost matrix and you want to compute the minimum transport cost or the distance without doing that. So the way people tackle this in the community is to embed the EMD metric into a simpler space. So simpler space meaning L1, L2 space or something like that, where we have where distance computation is super easy, and we have also well-known algorithms for approximate nearest neighbor search. So if you think about it, the mean proposed by WMD basically embeds this EMD metric into the L2 metric. So that's how they speed it up. And we'll see that quad tree and flow tree basically embed them into a tree metric. We'll see what a tree metric is. And embedding into the tree metric increases the efficiency by quite a bit. Any questions? Or we will move on to the construction of the quad tree next. Okay, so like I said, we have this initial metric M, which is the underlying metric over which the EMD is defined. So in the image setup, it would be the R3 space, let's say over L2. And we are embedding this metric into this. So there are well-known, there's this long line of beautiful theoretical work which deals with embedding an arbitrary metric into a tree metric. And we like trees because you can do a lot of dynamic programming and recursion on that. So there are really efficient algorithms that can be made to work on trees. So once we embed this underlying metric into a tree metric, then that approximates this EMD over this underlying metric to this EMD over the tree metric. So it's not a lossless conversion. There is some distortion that is happening. So we will discuss about that. But it's sufficient to say that this can be made to become a pretty good approximation of the EMD. And now there's some follow-up work where this EMD over the tree metric can be then embedded into the L1 space, which makes things really fast. So we will discuss these things one at a time now. And also, there are well-known approximate nearest neighbor data structures in the L1 space. So that's an additional benefit that comes out of using quad tree. So what is a tree metric? A tree metric is simply denoted by a tree where the points of the items of the set lie on the nodes of the tree, and the distances between the points are defined by the shortest path along the tree. So let's say you have this and this point. Okay, I have to use a pen. Let's say you have this point and this point, and the shortest path would be 5 plus 3 plus 1. And that's just what a tree metric is. So let's discuss a bit. So we are taking a brief detour now to discuss, to refresh some of the definitions, and then we will come back to quad tree quickly. So let's discuss about, like I said, there's a lot of theoretical work which deals with approximating any arbitrary metric into a tree metric. So how good is any such approximation? That is given by the distortion. So this is the definition where you have this source, let's say I will call this as the source metric and this as the destination metric. So you have the source metric space X with its distance function, and then you want to embed it into this metric Y, and it has a distortion alpha if this inequality holds. So basically here R is some sort of a scaling factor, which like because we care about approximately preserving the ratios of the distances. So R accounts for that. And alpha equals to 1 is the ideal case, where if alpha is 1, then any distance in X, any distance in Y is just a multiple of the distance, corresponding distance in X. So the distance ratios are well preserved. So that is called an isometric embedding. And now if the alpha starts increasing, then the distortion increases. So then we are, as it increases, we get more and more into trouble. So there's this, okay, so this is the definition of distortion. And now if we are, so how about embedding something into a tree metric? So this is a very interesting, use case that I found. It's very, it sort of very nicely incorporates the idea of randomized embeddings, which we'll discuss now. So let's say you want to embed a cycle into a tree. So you have a metric defined over a cycle. You have a set of nodes, which are the points on the n node cycle. And then you want to embed it into a tree. Okay. So how would you do that? It's obvious that you have to cut one of the edges of the cycle. But if you do that, then there's a order n blow up in the shortest path distances, because any 2 points which had their shortest path through that cut edge will now have to take the longer path around the cycle. So there's a order n blow up. So this is a problem, and the solution to this is to come up with randomized embeddings. So instead of cutting one specific edge, you choose which edge to cut uniformly at random. So what that means is you are building a distribution over the target tree matrix. And then you can put some probabilistic bounds on the expected blow up. So you can say that you can convince yourself with a little bit of thought that if you choose an edge uniformly at random, then the expected blow up in the pairwise distance is only 2 times, is bounded by 2. So which is the result which is shown here. So the first inequality holds naturally because the path distances in the cycle will always be less than the distance through the tree. But this expected distance in the tree metric, in the distribution of the tree metrics, will always be upper bounded by twice the distance in the original cycle. So this is an example of the area of randomized embeddings, and we will see some inequalities like this in quad tree analysis. So the goal is to embed any arbitrary metric space into this tree metric with the small expected distortion. So the alpha has to be as small as possible. And this is thanks to this, long work. This is a very inexhaustive list of citations, but the summary is that there are very tight bounds which say that any endpoint metric can be probabilistically embedded into trees with order log n distortion, where n is the number of points. So we are going to use this bound in our quad tree analysis, where we are embedding the metric m into a tree metric. So any question about this randomized embedding? Otherwise, we'll move on to the quad tree construction. So I'll zoom out a bit so that this page is visible to all. Okay. So let's look at how do you embed this endpoints into a tree metric. So yeah, so so let's say you start with these endpoints in the d-dimensional space. So for the purpose of the illustration, it will be these 5 points in the R2 space, and the distance can be either L1 distance or L2 distance. And the idea of the randomly shifted grid we'll see soon, but it's related to the idea of randomly picking a edge to cut in the cycle uniformly. So that randomness introduced gives us some expected distortion bounds. So we impose a grid on this 2D space, which splits the point. And the grid is usually like it splits the space half and half. So that's the construction technique. So if you have a side length of delta, then the length of this part will always be delta by 2, and so on. And now imposing this grid will, so as we are imposing the grid, we are also creating a hierarchical tree which separates the space. So we are starting with this 5 points in a single node, which are then split into these 3 regions, which contain the points under the new grid. We don't draw the empty grids just for visualization. So now we can again impose a smaller grid, which so this is delta by 4. It goes even smaller, and we stop when each of the leaf nodes has a single point in it. So this is how you embed this 2D space into this tree metric. Now, each of these trees, each of these edges in the tree, as you can see, have this delta by 2, have this weight, which is the side length of the grid that created that level. So initially you had this entire space of space containing all 5 points, and then you imposed a grid of length of side length delta by 2, which created this level, and hence the edge weights are delta by 2 here. So this is how, so as we discussed earlier in the tree metric, the tree edges have some weights, and this is how the weights are being assigned in this construction. So in this case, since this side length was delta by 4, so here this edges have delta by 4 weight. Any question here? So there should be one question, but yeah, so basically, yes.
I have one question. So the edge weights we are assigning sort of uniformly, right? Delta by 2 everywhere.
Yes.
So this will this not create issue if I have a lot of points concentrated towards the center of this grid and some points near the boundary? So what I mean is, if I have a blue point on, let's say, lower right corner of the first quadrant, and one more point in the upper left corner of the fourth quadrant.
So you are talking about this case, right? So let's say you have this grid, and you have a point here, and you have a point here. Yes, exactly. So this is a good point. So this is, this is just the case where you're imposed. So you have a set of points, and this is a very unfortunate case that you have imposed a grid in such a way that it splits these 2 close points into these separate quadrants. So first of all, the solution to this is to randomly wiggle this grid a bit before imposing it. So that's the first solution. That's where the randomized embedding comes. And the other insight, so there are some analysis to these worst case possibilities. The insight to this is that if the length is 2 to the power, if this length is, let's say, x, the distance between 2 points, x is very small, the probability that a grid of length, side length, delta by 2 will cut it is just x by delta by 2. And now this is usually much greater than x. So this is
assuming uniform distribution across the grid, right? I'm talking about cases that is more often occurring in practice where I have concentrated points and there are some outliers that are spread across. Typically embeddings and all, we have some outlier embeddings that are away, and most of the embeddings will be, for instance, will have norm close to 0, right?
Right.
So first of all, Indra, is it the case that the grid is thrown down uniformly at random? The point set is fixed, but the way I'm gridding it is random, right?
Yes.
Random and adaptive, is it?
Not adaptive, random. Adaptive is like some of the recent papers have tried to do it.
Okay.
So I think what you're saying is you have this cluster of points and you have a few outliers out here, right?
Correct.
Yeah. So basically, That's a good question. So what would happen if you split your grid like this? And this naturally puts a bunch of these points on separate quadrants. So what you would expect this to do is to, so form the grid like this. So if you have a cluster here, then the grid should be something like this so that they are part of the same quadrant. Yeah. That's so I don't know if they tackle this. So that's where, data sensitive grids come into play. So these papers don't do any data sensitive mechanisms for imposing the grids, but what you're saying is best tackled by having that data sensitive grids.
Okay.
So yes, there is definitely a performance degradation if the data is, so there is a performance improvement. The optimal performance happens when the data is uniformly spread across the plane. But yes, if it is concentrated on slightly one point, if a bunch of them, then it will suffer. It will definitely do that. So I think in the last year or so, there have been some papers which do this data sensitive tree embedding, where this sort of thing is then addressed. But I haven't read those. So I'll see if I can find something, I will link them. Yeah. So so the other thing is that in our earlier, so this is basically a very special type of tree. This is called, I think I have the definition later, but let me mention it here. It's called the hierarchically separated tree, where all the edges coming out of a node have the same weight. So as you can see, all the edges have delta by 2 weight. And the edge weights decrease exponentially by a constant factor. So you can say it's delta by 4, delta by 2, delta by 4, and so on and so forth. So this sort of, this has some special properties, algorithmically speaking, which we'll discuss next. So this is not your usual tree metric. And also, as you can see, every grid creates a separate, copy of the nodes here. So we stop when the leaf nodes have let's say there are 5 points, so there will be 5 leaf nodes. But every grid actually buckets these points according to a separate resolution, let's say. So this is the hierarchically separated tree construction. Now,
quick question, Indro. Sorry about that. Like, is this inspired from decision tree classification in any way, like the grid formation and then splitting into stopping at the leaf nodes when each points is different in each leaf node?
Hierarchical space partition has a long history. And, you might say that decision trees and this kind of thing come from the same common ancestor.
Okay, got it. Thank you, sir. Thank you.
okay, so once you have computed this tree, or rather you have mapped the 2D plane into this tree metric. Oh, I have written hierarchically separated tree. Now, like I said, it has a very interesting property that, the edge weights decrease exponentially as you go down the levels. So that allows for a bottom-up greedy approach for the matching. So the best, greedy strategy to have is to match the elements which are at the lowest levels, because they incur lesser cost. And then whatever, is mass is left, you keep matching them by going up the levels. So let's look at the bottom-up greedy matching in this case. So again, we go back to our earlier example where you have these 3 red points of 1/3 mass and 2 blue points of half mass. And what you do for the matching strategy is to go bottom up, and at the leaf level, let's say in the nodes C and E here, let me highlight. Yeah. So here you are matching the 1/3 mass that is available. And for that, in order to do the transportation action, your point has to traverse up this edge and meet at this common point. So that incurs that much cost. And then you see that there is some leftover supply of, so just a personal terminology, I am calling the red points the demand and the blue points the supply. So you have some leftover supply here, and then that keeps incurring cost as you pass it up the tree. Similarly, on the left hand side, you have this matching of 1/3 mass and then you have 1/6 left over. And these two 1/6 mass are being mapped to this 1/3 mass of B in the highest level. So this matching corresponds to the flow lines in the left-hand side image, where you are seeing how much mass is being transported between the 2 points. So basically, this bottom-up greedy approach translates to finding this shortest path matchings in the original space. And the optimal, matching cost is computed by, so you go over every, node of the tree or every edge of the tree, every element of the tree, and you multiply the weight of the mass, the mass which is being matched at each at every component, and then you multiply it with the edge weights. So here, since 1/3 mass is being matched with delta by, since 1/3 mass is being matched with delta by 8 cost, you multiply that here. And then since 1/3 mass is being matched here with delta by 4 cost, you multiply that here. And since the remaining is matched here, you multiply that. And this gives you the OT distance in the tree metric. So this OT distance is in tree metric. Yeah. So now, there's a follow-up work in the quad tree paper where they show that this tree metric is, so quick recap here. So here in the diagram, like we said, so we have seen this part right now, that this metric M is being embedded into the tree metric, and therefore the EMD over the original metric can now be approximated as the EMD over the tree, what we just saw. And then this follow-up task is pending, where we see how the EMD over the tree is can be embedded into the L1 space. So let's discuss that now. Yeah. So for the embedding into the L1, let's say we have this. So I have taken this diagram from their slides. So let's say you have these 4 points which have been embedded into the tree metric. And then you have this set of 2 points, and you have this set of 2 red points and set of 2 blue points, which look like this in the original metric space. These are the grid lengths. And the mapping of this 2 points here incurs a cost of 2 delta by 4, which basically corresponds to this transportation here in the original space. And this mapping incurs a cost because this blue point, because this blue point has to travel up this edge and this edge. So therefore, it incurs a cost of delta by 4 plus delta by 2. And since this red point has to travel up this edge, therefore it will incur a cost of delta by 2, and that's the total cost. And that basically corresponds to this longer flow path. So now, how about the embedding into the L1 space? Let this be, okay. Yeah, so just imagine this tree consisting only of the red items. So I can write this tree like this. So this is basically so I am specifying the edge weights in the nodes, and this has delta by 4 because that's the least edge weight that there is. And these points don't contain red points, so there's 0 here. And therefore, delta by 4, 0 and 0. And this has delta by 2 because the subtree under this node has only this one red point. So this has the delta by 2 value, which is the edge weight at this level. Similarly, this has delta by 2 because there is only one node here, and this has 2 delta because this is the highest level. So the edge weight here can be thought of as delta, and there are 2 points underneath it. So this is the tree for the blue items. This is the similar tree for the, so this is the tree for the red items. This is the similar tree for the blue items, where you have delta by 4 here, delta by 4 here. You have delta here because there are 2 red points here, each with cost no, delta by 2. And then you have 2 delta. So if you write this in the form of a single vector, which is, and you take the L1 norm between those two, you get the exact value as we computed here. So here you have 5 delta by 4 plus 2 delta by 4. Here you get 7 delta by 4. And this is basically taking the difference of these two vectors and computing the L1 norm. So what is the intuition behind this? You basically, in the original space, you have these set of 2 points, and hence, so when you consider the grid of size delta, that you forget about the inner grids and you just take the outsidemost grid, that contains 2 red points, and therefore the weight is edge length times the number of points in it. Okay, 2 red points and 2 blue points. Now when you specify this grid of side delta by 2, which is the second level of grid, then let's say this grid has only 1 red point in it. So therefore you multiply delta by 2 with 1 here. Similarly, this smaller grid has 2 blue points in it. So you multiply the side length by the number of points. And this is how you so this tree is basically for visualization purposes. This vector is directly created using that technique, that you recursively impose a grid, and every time the grid results in a histogram of the points. So every grid being imposed on the 2D space creates a histogram of the points. And now you multiply the histogram with the side of the grid length. And that concatenation of all the grids that are created gives you a L1 vector. Questions about this? Right. So now this thing can be, you can see that this can be very, very sparse. So the number of, let's say the support size, the number of elements of the set is S, and we have a bunch of such sets. Then let's say we have N sets, and each of them have S elements, and therefore you have NS nodes in this tree. But only S of them corresponding to a specific, let's say, red set of points will be there. So it's a very sparse set. So now the problem becomes finding the L1 distance between two sparse vectors, and that is extremely fast to compute. And you have very fast k-nearest neighbor, approximate nearest neighbor search algorithms to do that. And that was the main contribution of quadtree. We'll do some analysis as to why this thing suffers in higher dimensional spaces, but this is the basic idea about the construction and the embedding. Okay, any questions? Okay, so remember we discussed about distortion bounds. So this sort of embedding from the underlying metric to the tree metric incurs some distortion. So quadtree does some analysis for that, and we will now look at them. So this is basically I have taken this snapshot from the paper so that we have some understanding about the notation. So this is basically doing what I said earlier. So 2 to the power i's are the edge lengths of the grid, and the vi is the histogram that is created by imposing that grid on the set of points. So like I said, you take the histogram and you multiply it with 2 to the power with the edge length. So 2 to the power I, because so let's say this is the tree from our, so this is actually exactly the tree from our earlier case. And we designate the last level as vi minus 1, and then v0, v1, and so on and so forth. And the weights of each of the level is 2 to the power minus the subscript of v. So 2 to the power minus 1 is the last level. So the reason for that is that given any data, you can always scale it so that the minimum distances between any two points is 1. And therefore, it's easier for the analysis that way. And if the minimum distance between any 2 points is 1, then the smallest grid size that is necessary is 1 by 2, which is 2 to the power minus 1. So that's how they do the analysis. So this is the new notation where we start with v minus 1, which has 2 to the power minus 1 sized, grid. And then we move on to 2 to the power 0, 1, 2, and 2 to the power I. Okay. And P here is the original point set in the, this is basically the set of points that we have embedded into this tree metric. And like I said, there are order of cardinality of P times the height of the tree. So the height of the tree will be log delta, where delta is the largest distance between the pairs of points. It's because at every step you are halving the size of the grid until you reach 1/2. So log delta levels will be there in the tree. And there are these many non-zero entries. So we have two sorts of distortion bounds. So there are, first of all, we will have an upper bound on the estimate of the, so we will have two sorts of bounds. So here, the first bound is that the EMD, so the actual EMD, so let me write it like this. This is the actual EMD distance between the two sets of P and Q. And this is the tree metric distance. So we want to bound that our tree metric distance is within some range of the actual EMD. The actual EMD is within some range. So we want this C constant to be as low as possible. So how do you do that? So I won't go too much into the details of the derivation, but basically what they say that in this, the way they do that is that in this last layer, since all the points have their own room or have their own cell in the grid, so therefore the distances, each of them have at least 1/2 distance to travel in any direction, no matter what sort of matching you do. And there are 2s such points. So this is the cost that is incurred in the last layer. In the second last layer, this is basically V0 is the histogram which is being generated by imposing the second last grid. If you can match these, so V0P minus V0Q gives you the number of points that are matched, this divided by 2. So these are matched, and these have already paid their dues in terms of cost in the earlier layer. So they don't actually contribute any more additional cost to it. But the remaining S minus these number of pairs will now have this 2 to the power 0 times this distance to cover. So now here you see there is a square root of
What's
2
the
term.
yeah.
Yeah. So basically that is because the original quadtree paper was in L2 in R2. Okay. So now for any, so this is just an upper bound approximation of this. If there are 2 points in this grid and it's the side length, maybe anything, let's say delta, then no matter what the distance is, they assume the worst case and do there is a square root delta distance, right? So now here's the problem. So since the original quadtree paper was in 2003 and they were working on low dimensional point cloud stuff, they got away. So they agreed that this thing was horrible in higher dimensions, but because the square root term can essentially become D, because the diagonal of a cube in D dimensional space under L2 distance would be square root of D times delta, and under L1 distance would be D delta. So there is a hidden D here in the constant term. So that's why this bound is pretty much, this is a very bad situation, because that's basically saying that my tree metric distance can be D times, smaller than the actual EMD distance, where D is the dimension. So this loses all. So this is a very high distortion for higher dimensional stuff. Okay, so this is the first bound that we have. And the second is the other, which says that, the tree metric. So the second bound basically tells us that whatever the predicted distance is with the tree metric is within at most some range of the actual EMD. So again, just to recap, this is EMD actual, and this is tree. Let's call it EMD tree. So it basically says that the tree distance is not contracted too much by this EMD from the actual EMD distance. Wait, is that? Huh. So okay, so again, so there was this earlier I was discussing something where this is a very unfortunate case where these 2 points are very close to each other and still they fall into separate grids, and therefore they have to give, like, instead of this small distance they have to give this large, let's say, delta by 2 cost. So this is a very unfortunate setup, and that's why the idea is to shift the grid randomly. So if we shift the grids randomly, then we can have a reasonable bound on the expected distance that is returned by the tree metric. So because of this, so again, I'm wondering if to go too much into this, but there are two interesting points. There is at least one very interesting observation here, which is useful to us, that the probability of an edge of length L being cut by the grid I is bounded by L by 2 to the power I. So let's say the distance between these 2 points is L, and you have this grid of length 2 to the power I, then the closer the points are, the lower probability event it is that this grid of length 2 to the power I will cut it. Exactly. So this helps us get an upper bound on this, get a bound on this worst case possibility under the randomized grid setup. So that is one observation. And the second is that every time something unfortunate like this happens, that contributes at most to twice the cost, because anytime this grid is cut, anytime this edge is being cut by the grid, that contributes at most 2x cost. So basically it will have to traverse one hop up the edge of the tree and then match instead of getting matched in the same cell. So these two intuitions basically gives us the bound, which is at most 2 times the 2 times log delta times the actual EMD cost. Okay, so the other thing was that in 2-dimensional, the number of levels in the tree is log delta. We have seen that before. But in d-dimensional space, that becomes log d delta. So as you can see in their analysis, they only had log delta, 2 log delta times the actual EMD distance. But in the d-dimensional space, that will become d delta, which is not bad. I mean, we are okay with that. And that's the best bound till now as well. So in summary, in this IT03 is the paper in Dick Thapar 2003. So the summary is that we can get, by these distortion bounds, we can get a order of C log delta approximation for R2. And in d-dimensional space, we have a d log d delta approximation, where log delta comes from the second thing and d comes from the first lemma that we proved. So as we can see, this is not good for d-dimensional space. So what's the answer to that?
Inka, I have one doubt. Do we have any properties on the ranks of so let's say I take a point and sort other points in according to the distance between them. Do I have any property that sort of guarantees that this rank is preserved?
So I didn't get about the rank.
Yeah. So what I'm telling is, let's say I take a point I and compute distances to other endpoints, and with respect to this distance, I'll get a rank order, right? What I'm asking is, if point ij is closer in according to earth move distance, do we have any guarantee that they will be closer in this tree distance as well? The scale is different, but is the ij being closer than ik, is this property being preserved?
Yes, so that guarantee comes from the distortion bounds. So acid, is there any bound on that with respect to ranking?
Ranking, it's kind of always tricky because it's probably easier to establish like distortion because now that itself, I don't know, you can create a lot of tiebreakers within an narrow score band. Not sure, have to look it up. So for example, in case of say page rank, I think rank stability is harder to ensure than score stability. So my first reaction is anything like what do we call it? Foot rule distance or something, number of inversions. Maybe pretty hard because I can, if I can place the points adversely, I can create a situation where small omega of n squared inversions happen, or with one query point omega n inversions happen, maybe possible because of the inaccuracies from the tree metric. Interesting question. Okay.
Yeah, I'm asking this because if we don't have that kind of property, right, the optimal transport computed in both these metrics can be completely different.
So optimal transport doesn't really care about rank order. So as long as you stay in the score domain or distance domain, if tree matrix preserve distance to within some factor, then your optimal transport may be preserved to some other related factor. But ranks are a totally discontinuous thing, and pretty much anything can happen there. The transport plan doesn't depend on the rank, it depends on the costs. And if the costs are wrong by some factor, then your optimality is also disturbed by some factor, vaguely speaking.
Yes, sir, yeah.
So let's talk about how some future papers have dealt with this high dimension case. So there was this paper in 2008 by Andoni Indic and Krautkammer, where they sort of, so till 2008 the general notion was that we have this sort of approximation guarantee d log d delta. But in this 2008 paper, they showed that it's possible to get this down to log s times log d delta, where s is the support size. So what they basically said is that in the high dimensional spaces, as long as you are bound on the support size of the set, then things are not so bad. So s is the maximum support size of the set. And they basically showed these two inequalities. Again, like before, the earlier two lemmas, we have two new lemmas. So this thing is same as before. So this log d delta thing that we showed earlier, that still holds. So they confirm that. And additionally, they have this bound that based on s with a probability, which is 1 minus 1 by s, which is with a very high probability, the distance which is proposed by the tree metric t between these pq points is within certain range of the actual EMD. And that range is given by this very small constant. So we will look at the proof now, or the basic idea. So the central insight, so this 2008 paper was actually for a different, I think slightly different problem, something involving randomized communications. But in there, they also imposed a hierarchical grid on the set of points. And their insight was that given any 2 points, the probability PL that the points fall into the same grid, the same cell under a grid, lies between these two ranges. So, I mean, and they say that it's very easy to see that, but I tried staring at this to convince myself of that. So the left-hand side you can see follows from, so this is the probability that things fall within the same cell. And this thing we have seen before, x minus y by 2 to the power L is the probability of getting cut by a grid, and 1 minus that is probability of falling within the same cell. So that sort of makes sense. And then in the RHS, they have this exponent term. So I'm not really sure how they came up with this. E to the power minus x minus y by 2 to the power L. So this, if x minus y is higher, then this goes down. The probability of getting falling within the same cell goes down. But why this specific formulation, I am not really sure. Anybody has something to comment on this, please do so. So if we like take this as the truth, then we can actually set a delta by, let's say
So
the
could
delta
it
is
be,
equal
could
to
it
this.
be, so it looks like a sum in the exponent, so they're multiplying something. So could it be like a pessimistic or optimistic probability expression under the dimensions?
It looks quite tight, this x minus y, this distance by 2 to the power L, and then exponential and taking minus. So I was trying to find something using concentration inequality, but doesn't seem so.
Yeah, I mean, I
How many
also don't find it.
dimensions? What dimension?
So they don't. So any d-dimensional space, they don't mention the dimension here in this. No.
So this x minus y L1 is basically xd minus yd absolute value in
YD.
each dimension, right?
Yes.
Exactly.
So in 2D, it's just a sub base parts perpendicular.
I think we have this inequality. 1 minus x is less than exponential minus x.
Oh no, that's not the problem.
No.
The problem is p less than equal to exponential minus x.
Ah.
I was wondering if they're just multiplying through dimensions and then bounding something. Like for them to be in the same cell in the first dimension, they have to be in the same cell in the second dimension, they have to be in the same cell and so on. And then they're doing something about that.
Right. Right. So if you have this, then basically if you like sort of set delta to this value, then you can get like log. So you can take. So you can get this thing. It's pretty simple to do. So you are taking the log and then you are taking the minus, which gives you log 1 by delta. And then the 2 to the power L goes this side and that side. And so you have this thing, right? So basically, anybody saying anything? Okay, no. So then if you just put this delta here, then you have this inequality that for any pair of points under the tree metric with, so delta, remember, is a very small value. Okay. So let's say delta is, let's have an example. Let's say delta is 0.01. Then with probability less than 0.01, this item here becomes 1 by 2 under that delta 0.01. So with a very low probability less than 0.01, the tree metric is within at most half of the actual distance. Tree distance is within at most half of the actual distance in the original space. So this is the bound that you get. And now, given this bound between a given pair of points, for a finite support set, P and Q, you have S square such pairs. So S square such ways of messing up this probabilistic bound. So you take a union bound to get the probability over the sets, distance bounds over the distance.
Pessimistic, right?
Yes, it is. Yes, it's the pessimistic one. So yeah, so that union bound gives us this sort of thing, where with probability, 1 minus this summation over delta, where delta summation is over the number of pairs, this bound holds. And if you set delta to 1 by s cube, let's say, then here you have 1 by 1 minus, so number of pairs is s squared, so you have 1 by 1 minus s in the RHS, and here log 1 by delta becomes log s. So this basically gives us that inequality bound, that with a very high probability, I being 1 minus 1 by S, you have the tree metric within this very small multiplier of the actual distance. So basically it says that the tree metric does not contract too much. It remains within this half, let's say 1 by 2 bound of x minus y. So yeah, so this is their analysis for the finite support. So I have printed out the summary from their slides. So this was the original insight by the 2008 paper, which translates to the quadtree analysis by this, which tells us that instead of the d log d delta, we have log s times log d delta. Bounds on the EMD as long as we have finite support. So now what that means is that we have a s log s times log d delta approximation for the nearest neighbor search, but there is still one problem where, like like you said, it was overly pessimistic. So let's say you have a database of n distributions. So you have n times s square ways of messing up that union bound. So when you are doing approximate nearest neighbor search, this bound actually suffers, and then there's this additional n term inside this log instead of just the s term. So they have shown that if the dataset size increases, then quadtree suffers because of in practice as well, which is given by this bound. So okay, so this is like the story with regards to quadtree. And now the final part, which is the flow tree, which is a very minor hack on quadtree. And we are towards the end of our time as well as I think I can finish it quickly now. So in flow tree, what happens is they are computing the same. So there are two aspects to the quadtree computation. One is that there is the flow, which tells us how much mass to transport from one point to another. And then there's the actual cost computation. So in this case, the optimal flow is computed on the tree using the quadtree method, but the total cost is computed according to the original metric. So this is a recap of the quadtree. So in quadtree, you remember we did this where we are computing the flow in green, and then we are multiplying it with the edge weights to get the cost in the tree metric space. What flow tree instead does is it gets the same flow ft, but then it computes the distance in the original underlying metric space, not in the tree metric. So what this means is that this is no longer an embedding. It can no longer be embedded into the L1 space because we are so embedding into the L1 space was predicated on finding the distance in the tree metric because we are embedding the tree edges into the L1 vector. But since it's no longer doing that, it's computing the distance in the original space. So it can no longer be an L1 embedding. But what they say is that since the flow is computed in the linear time algorithm by the greedy bottom-up approach, it is still an ordered n method. But in practice, it's much more accurate than quadtree, but it suffers. Although it's not as bad as quadratic time, it suffers with respect to quadtree in terms of time complexity. So the time complexity is in fact given by this, where you have this log d delta times s because there are s items in the leaf, and then you have d delta levels of the tree to traverse. So computing the flow takes this much time. And then since you have this x minus y distance, this LP distance to compute in the original space, each such distance computation takes order d time. And you have to do it s times. S times because every time, so given two sets of s items, every time you match one item with the rest, let's say you have a demand set and the supply set, either the demand is completely fulfilled or the supply is completely exhausted. So every time you match, you eliminate one of the items from the 2s possible items. So there are at most order s such distances to compute. And so the time complexity is given by this. And now the thing is that, so here I am a bit again, so unclear, but what they show is that because this flow tree, so in the flow tree, you will notice that it is always prone to overestimating the actual distances, because the tree metric flow, green F, can be a suboptimal matching. So it always overestimates the distance. It cannot underestimate the distance. So since there is this one-sided error, so that sort of means that when we are taking the union bound, then we don't have to, we don't have to consider all n times s square items. Instead, we only need to take union bound over the s square distances between the query and the actual true nearest neighbor. So that sort of eliminates this dependence on n. And they show experimentally that flow tree does not suffer when the dataset size increases.
Yeah, there's something else though. I mean, this pessimism also involves the fact that, okay, in high dimensions, all kinds of crazy things happen, but a metric is still a metric. And can you create so many adversarial pairs? I mean, you see what I'm saying? I mean, if the original space is a metric in however many dimensions, then the fact that you overestimated this and you overestimated that automatically means you overestimated something else, something like that, right? Why do I have to account badly for all pairs?
Right.
That's something I don't understand yet.
Okay. So yeah. So in that, right. So yes. So I guess some sort of similar reasoning tells us why only we need to consider the closest set for the adversarial setup. Yeah, so let's quickly just cover the experiment part. So like I said, so here they just check, with the increase in n, they have created a
I'd just like to
synthetic.
make, sorry to interrupt, just one quick comment to Lokesh. For example, in nearest neighbor search, the theoretical formulations, they always say, if the nearest point is at a distance of so and so, I'm not going to guarantee anything about where that point goes in the ranking. I'm going to give a point whose distance is not too much larger. So this goes back to the ranking thing. I think ranks are very hard to guarantee. So all you can guarantee is what you get is near enough, not where did the true nearest go. Go on.
Right.
Yeah.
So basically, if you have this query point and you have this true nearest neighbor point, then what you can guarantee is that whatever point is proposed is within some radius of this actual. So this is actual and this is c times actual. And this is all you can guarantee. You can't say where this point is being estimated. So yeah, so basically in the first set of experiments, they show that, so this red denotes flow tree and yellow is quad tree, and with increase in n, they have synthetic data. By increasing the dataset size, they show that the accuracy of quad tree falls down, where accuracy is the number of, so they given a query corpus set, they pose the nearest neighbor question, they ask the model to retrieve the nearest neighbor, and accuracy is the percentage of times it achieves success. So they show that the accuracy drops. So that's the first experiment. The second is some table that we have seen before, so I'm going to skip over this. So the third thing is the individual experiments where they are checking the, so here accuracy means precision at k. So so let's say the system is asked to identify the top k nearest neighbor items, and it proposes some sort of them. So sorry, it's recall at k, not precision at k. So whatever top k items being proposed by the system, how many of the actual ones are being returned by the system. So there is this big gap, as you can see from this plot, that synchron is, so the number of candidates, the k value is at the axis, x-axis, and so synchron, all the n square methods are right up there. So they are extremely accurate. So within the top, for less than 100, they're pretty much at close to 1. For k less than 100, and the order n methods suffered greatly. There's a significant gap, And now float tree is right up there with the order n square methods. And now if you zoom into the left-hand part of this plot, so earlier the left-hand part was showing 100 and so on. Now we are looking at the top 30 recommendations by each of these models. Then they are saying that, see, float tree is a linear time algorithm. It's significantly smaller than, sorry. So it's significantly smaller than, lesser than the order n square methods, but its performance is comparable to them. Noteworthy is that Synchron is still, much better than float tree, but it's slower as well.
So here each point is in a high dimensional space, is it?
Yeah, so this 20 news is a high dimensional data set. So I am not sure how much. I have to look. I have to check the paper, but it's significantly more than, I think it's 60 or it's more than that, perhaps.
So here,
ordinary word space could be thousands.
Right. So what were you asking?
Here we are finding distance between documents, right?
Yeah.
Where each document is the probability distribution over word embeddings.
Exactly. So for precision at 1, you have a database of documents, and you are being asked to find the closest document.
Okay.
And precision 5, you are asked to find the 5 closest documents. So yeah, so these are the individual experiments. And now this is for scalability. People usually go through the pipeline route. So first of all, given this initial data set, you have this very crude order and approximation, which is prone to mistakes, but it filters out the most obvious non-candidates at the early stages. And then let's say you have K1 candidates at the end of the first crude approximation step, and then you give them into the progressively slower yet more accurate models. And therefore you have this sort of hierarchy. So if you have K1 candidates from this first level, and then you filter them down to K2 candidates, and at the last level, you have the exact Wasserstein computation model to get the true nearest neighbor. And the usual setup is to tune these values of K1 and K2 so that this overall pipeline takes as less time as possible. So the details are this, that in the bottommost level, they usually use the mean or the quad tree, and they found that quad tree is better than anything else for the fast and crude approximation setup. The slower and fine approximation are, they have a couple of variations. So this is the last plot that we are going to look at today. So as you can see, so this y-axis is the running time, and each pipeline, they are color coding the component, the time taken by each component. So the slower component takes the least amount of time. The yellow blocks by quad tree is the fastest, and they take the least amount of time. And then in the second stage, if you use the relaxed WMD versus you use some other measures. So as you can see here, if they insert this flow tree component here after the initial crude stage, then it filters out a lot of the item. It filters out a lot of the non-candidates and is able to give a sufficiently small set of items that the subsequent stages happen much faster. So what they're showing is introducing this flow tree block reduces the overall time of the pipeline in all the cases across a bunch of different variations. Yeah, so this is their observation. They got 3.x7 speed up on one of the data sets for recall 1 and recall 5. In fact, and another observation is that the Synchron measure is Synchron algorithm is accurate enough that you don't have to do exact computation at the end of it. The Synchron is able to identify the true nearest neighbors by itself. But even in those cases, just adding the flow tree reduces by their time a lot, and they get a 7x speed up. Okay, so this is it for today. I mean, this is what I had. Anybody wants to make any comments, questions? Or...
So did they show any kind of trade-off?
Trade-off as in runtime versus accuracy? No.
Yes.
No.
Okay.
They just had this. So here, basically, you can think of it in terms. So basically, here they have this. They are tuning K1, K2, K3 such that the pipeline takes minimum time to get the correct result. So here you can have some sort of a time versus accuracy idea. Because each of these columns or each of these pipelines is ensuring that 100% correct result is being obtained.
Okay. Okay. Okay.
This is it. So thanks. Please get in touch with me if you have any follow-up questions. I have to yet link the source papers. I will do that and upload the PDF.
Okay.
Thank you.